Well, welcome to Quadrivic Mathematics with Daniel Jones, Chris Garcia, and our wonderful Bill Stutzman is also here. We are at book the fourth. Very excited to share the next stage of this journey. Take it away, Daniel.
Okay, yeah, book fourth. So we have laid the foundation with sets, as you guys know, and with relations. And in the last book, we talked about multitudes, as opposed to magnitudes. Multitudes being the how many, whereas magnitudes, which we're going to talk about in geometry when we get there down the road, talks about the how much. And like I said before, modern mathematics tends to conflate those two, and I'm kind of on a mission to separate those two out the way it's been for hundreds and thousands of years. Because even our natural languages distinguish between the how many and the how much. I think our mathematics should as well. And I think there's consequences to learning mathematics this way as opposed to the other way. In particular, having mathematics match your natural languages makes it much more intuitive for students. It makes it easier to learn. Takes longer to learn, of course, because it's not as streamlined when you only have one system as opposed to two simultaneous systems. But it's much more in line with how the real world actually works. And so there is a case to be made for quadrivic mathematics being more intuitive and therefore more restorative to the soul, I'll say. There's been different ways to express that over time. People have talked about mathematics having an elevating effect. This is a long time ago, thousands of years ago, mathematics have an elevating effect, primarily because it gives you the language by which to describe the world around you. And when you take that away by not distinguishing between arithmetic and geometry, I think we do our students, at the very least, an in-service. So book the fourth is kind of like a transitional book. It's not very long, it's very short. It defines basic things like what's a prime number, what's a composite number, what's a factor, what are factors, multitudes, things that you would learn in the seventh grade math class, or maybe even the fifth, sixth grade math class, maybe also even in the ninth grade math class. So it's nothing surprising, nothing revelational, but something that needs to be covered. And so we're looking at it from the standpoint of the definitions we've already defined. In particular, in book 3, we defined number. We know what numbers are now. We have numbers 1, 2, 3, 4, 5. Remember, in this system, things like 1/2 is not a number. We haven't defined 1/2 yet. 1/2 is actually a relationship between two numbers, or even things like -5. I don't consider -5 a number, which is very much contrary to what is proposed in modern mathematics, right? Most math teachers will say, well, -5 is, of course, it's a number. The integers, in that sense, are a subset of the set of all real numbers. Therefore, it's a number, that kind of thing. But I say, okay, but then first give me a definition for a real number, then maybe you have a case. But I say, why not define things from the smallest element and get bigger, as opposed to start with the real numbers, which are undefined. Remember, in the classical world, we have to define our terms. That's one of the tenets of a classical education. You have to define your terms. I say, even in mathematics, we should be defining our terms. So if you haven't defined an integer, in my opinion, once you hit the secondary mathematics curriculum, you probably shouldn't be talking about an integer until you've defined it. And so again, these terms for book 4 are just to kind of round out our understanding of a number. We've defined number in book 3. Now we say, okay, let's look at more specific numbers. Let's look at prime numbers. Let's look at composite numbers. Let's look at the relationship between these different numbers. Now, one thing I also want to point out, we've been only going through the definitions in this series, right? We take book the first. What we read in book the first wasn't the entire book the first. That's just the list of definitions by which you start book the first. Okay, we haven't really even gotten into the theorems. We haven't even really talked about theorems at all. Maybe we should do that at some point, Chris, I don't know. But the idea for these videos, though, is just to lay the foundation to show the world that, yes, you can define your terms in mathematics. It is possible, and it is possible at the 7th grade level to talk about things that you see in a 7th grade math textbook and define those terms. That can be done, and that's what we're doing in this series, showing that these things can at least be defined. Then from there, you can prove all kinds of theorems with those definitions established. Lots more to say, but I'll stop there. Let's get into these definitions. Once we finish book 4, then we'll get into book 5 right away. We'll get into, I think it's what do we mean by an integer. I think that's how I have it sequenced. Just check myself real quick. Integers, and then followed by fractions, then the rationales, and eventually get to the real numbers in that sequence. Bill, Chris, or Kathy, anything you guys want to say before we start reading?
No,
No.
yeah, I'm excited to know that that's helpful to think that these books, of course, have just been the list of definitions this is all giving us something to work with. It's not the entirety of book the first or book the second or book the third. That's a very helpful distinction
Helpful
to make.
information that I forget to mention. For those of you who have read Euclid's Elements, these books are modeled after that format, where he first lists the definitions and the axioms for each particular book,
Yeah.
and then he proves the theorems. It's the same format as Euclid. Euclid's definitely one of my heroes. I see his work as monumental. He changed how we think about mathematics. I mean, we don't even realize how much he did for us. And so I'm modeling it, like many mathematicians before me have also done the same thing. They have modeled their work after
Yeah.
Euclid. Okay, let's jump in. So Bill's going to read the definitions. Chris, maybe put the camera on Chris, I suppose, for this segment, Kathy, and let's jump in.
All right. Book the fourth. Let the following be defined. First, if one number is the product of two others, then each of the two is said to be a factor of the number, and the number is thus said to be a multiple of each of the two.
Good.
Since,
And
oh, okay. Yeah.
and yeah, I think Bill was about to read on. I'm going to let Bill know because I forgot to tell him. Just read the definitions. We'll let Chris take care of all the details. So if you can discern where the definition
Perfect.
starts and stops, that's all
Yep.
we need to read.
You got it.
Okay, so right here, first thing that jumps out, one number is, if one number is the product of two others, then each of the two is said to be a factor of the number. So we, of course, go back to the definition of a product, which I have pulled in here from book 3, where the product of two numbers, a first and a second, is the sum of the first and the second. If one number is the product of two others, then each of the two is said to be the quotient of the product and the other. And we have some illustrations kind of breaking down what that meant before, just as a refresher. So in this example here, the product of 5 and 3 is the sum of 5 threes, or in other words, 3 5 times. Or alternatively, the product of 3 and 5 is the sum of 3 5s or 5 3 times. So these are the two kind of ways you can lay out kind of what 15 is. And so tying back here, then we would say that 5 and 3 are factors of 15. And 15 is thus said to be a multiple of 5 and 3, each of the two. Questions? Comments?
Good.
I
Very
was
clear.
it makes sense, but it is kind of the same as what we've been taught. So would you add any nuances to that would break out of I memorized that as a kid? What does
No,
that mean now?
yeah. Thank you, Kathy. That's actually the whole point. Is that the way we learn to as kids is so intuitive, and in fact, the way that we stack things is how we've been doing it for hundreds and thousands of years as people, right? The point is not to be so like different. The point is just to give definitions to things that we all know and have learned since childhood. One thing I will say, Kathy, this definition of 3 times 5 is not the definition of 3 times 5 in our modern secondary textbooks. You'd be shocked because that seems like that's what we all learned, right? And that's how it should be. That is not what 3 times 5 means in pre-algebra today. And that's kind of my whole point. It's like, wait a minute, this is what we all know. And even Kathy's like, well, we know this. This is so obvious. And I agree. So why don't we use this in 7th grade? Why do we suddenly change the whole system of what a number is? I don't think we should. So the fact that it's so simple and straightforward is its profundity, especially since that's not what's done in 7th grade today.
What would be an example of what is done today?
Ooh, that's a big question. So I will do my best to answer that question. So for example, well, the reason that 3 times 5 is not defined this way is because 3 isn't this same entity. in modern mathematics and the secondary curriculum that modern mathematics is seeped into, 3 is actually either seen as a point on a line, again, the conflating of arithmetic and geometry, or it's an abstract entity that follows certain rules. And 3 times 5 becomes an axiom as opposed to a definition. You notice that we were able to define what 3 times 5 was without having to bring in any axioms except for the ones that are for set theory, right? And so Bertrand Russell actually has a quote. He says, to add axioms that are not needed is basically thievery. An honest labor would be to not use axioms, just define things as they are. And I agree with Bertrand Russell on that. Of course, there's things we disagree with Bertrand Russell on, but on that point, on his objective to define terms as opposed to bring axioms in, is a very classical idea. So the reason the 3 times 5 is different because their 3 and their 5 are not the same as the 3 or the 5 in this context. Does that answer your question, Bill?
I think so. So maybe let me restate it the way I think you're saying it. In modern current mathematics, 3 is given, it's not a description.
Yeah.
And it is given, 5 is given, it's not describing a reality. And we are given 3 times 5 is 15. Take it, deal with it.
Well,
rather than
close.
Yeah.
We're given something called Peano axioms. No, well, it depends on the system you're using. It's not necessarily straightforward. So it's more like it's defined that 1 plus 1 equals 2, and then 2 plus 1 equals 3, similar to what we did, and therefore 3 times 5 equals 15. But those things aren't describing anything real, like you said originally. It's not that it's given that 3 times 5 is 15. It's more like 15 is the number that we're going to, I guess it is what you're saying then. I don't know if I can explain it better.
No, that helps though. I mean, I know there are examples where, as a kid, count the rows and columns of the ceiling tiles, and you can multiply. You can understand there are 3 rows of 5, and so in that, oftentimes we turn to examples to demonstrate it, but we're not shown that as a foundational principle necessarily.
Yes, it's not the ontological reality of what we're dealing with. Yeah, exactly like you said. We're looking at those as examples for how we can understand these things, as opposed to looking for them as examples for what we define, which is what you just said.
Perfect. Thank you.
Yes, good.
If we're all clear there, we could probably move on to the next one.
All right. Ready for the second. Second, a number is said to be even if it has 2 as a factor and odd otherwise.
Okay. So even if it has 2 as a factor and odd otherwise. So let's see if I can make an example here. I guess the easiest example would be 4. So let me pull our 4. Where we have 2 and 2 as the factors. Actually. So the number 4 would be even here because it has 2 as a factor. The number 2 as well would be even because it would have 2 and it would have 1. And I'm sure we can all come up with plenty other even numbers. But I like that this is just, it's a simple concept, it's a simple definition. But it is a definition in this system because of the groundwork we've laid already.
Chris, I just want to add that I think it's helpful that you put the 2 and the 2. Originally in book the 4th, it just has 1 factor written in the description. So I guess I'm thinking, would you list all the factors of that number, or to show that 2 is one of the factors or not. So for example, 4 just has the number 4 next to it in the book the fourth, as opposed to the 2 and the 2. So you don't see that. I mean, we know
The
the factor
factors.
2 is there, but I just in that example, it's not there. Same with the odd
Yeah.
numbers. You don't necessarily know that the factor of 1 is there unless you just know that the factor of 1 is there.
I think the other
Yeah,
thing that I go ahead, Chris.
no, you go ahead.
The other thing that I appreciate, and you could still go there on this example that you've set up, but I appreciate in the book currently that all of the sets are arranged in 2 horizontal rows that are even. And so the way you've begun this example, I would expect any further examples to be in 2 columns. But in either case, they are matching rows or matching columns in which I can visibly see pairings. I can see that that is 2 sets of 3 that are the same. I can see that it's 2 sets of 6 that are the same. However it is, that physically demonstrates a rectangular shape for me.
And what you guys don't know is that the ancients loved that fact, exactly like Bill describes. They didn't necessarily think of these as multitudes per se. They actually thought of the set itself as a 2. So they really thought like 2 was something physical, like 2 things. And so they're even more concrete than we are in our way of thinking. But the idea of stacking, just like you said, and seeing those relationships conceptually, visually, and geometrically was a very classical ideal for a long time.
Yeah, and I think that it is doing something to the student, unbeknownst to the student, to see them organized uh, consistently that way.
Yeah,
And then you could ask the question, well, how come it's the same whether it's organized vertically or
yeah,
horizontally?
yep,
But that's another question,
yep. That's a question of what is the commutative property, right?
right?
Exactly.
And then I guess I'll also pull in since I prepped it. Yeah, I so focused on even. We also have odd numbers. So if 2 isn't a factor, then it's odd. And you can just see that at a glance when you lay them out, just like you guys were talking about.
By the way, all these definitions I would have my students debate. I would say simply, what does it mean for a number to be even? And they have to come up with the definition. We're just taking the shortcut, right?
One of the things that was always cool about that approach in class is sometimes you would come up with another way of defining that was correct.
Yep.
Sometimes you would even organically come upon a more elegant or precise definition, and it would just get adopted into the curriculum.
Mr. Jones would steal it. Absolutely.
Yeah, very, very exciting as a student. Actually makes you feel like you're really a mathematician, kind of part of
Yep.
the community, not just an outsider peering in.
Mm. I was there for that one, you think?
Yep.
Yeah, I would be intrigued too by the way these odds are represented, in which the bottom row or the top row, depending on how you want to look at it, is shifted so that uh, the lower row fits in between the extras of the top. But you could arrange it so that the extra is hanging over the edge of the same shape that it was before. Either way, you've obviously got a different shape.
Bill, an
But I do
interesting idea
appreciate,
is if you do the hangover one, then it shows the factor of 1. So if you were to line it up and then have the extra one there.
but I do like how this is represented with the outline form of the shape for the extra. That's nice.
You want to move on?
Okay. Third, A number greater than 1 is said to be prime if its only factors are 1 and itself, and composite otherwise. Composite numbers are also said to be rectangular.
All right.
Again, the idea of rectangular numbers is a very ancient classical idea. Go back and if you look at the literature, the ancients loved square numbers and rectangular numbers and planar numbers and pentagonal numbers, perfect numbers, lots of terms that they studied when looking at number.
Yeah. So like once again, this is just kind of something that organically like it's just there. You see it, the squareness or the rectangular of it, which is something that I had never really thought about. Just like reading through the book, I was like rectangular and I'm looking at the examples and I'm like, oh yeah, that makes sense. So of course, greater than 1 prime if its only factors are 1 and itself. So we have the prime numbers here. Um, well, the first few, 2, 3, 5, 7, and 11. And you really can only lay them out in a line this way. And if you were to have those rows, right, you'd get like with 11 here, you see it's not that square, well, that rectangular shape. Um, and then if it's not prime, it's composite. And we have that note here, right? Composite numbers are also said to be rectangular, which is exactly what we were talking about. It's just something you can see at a glance and know. Once again, a definition and not an axiom.
So above, 11 is represented in a different visual format. When it's being demonstrated as odd, it's not. And of course that's fine because you can arrange 11 in a number of ways. But here, 11 is organized as one row because it can't be made rectangular.
Yeah, and I
I
think
assume. Yeah.
that's also to call attention to the fact that its factors are 1 and
Yes.
11.
Yep. I like that. I like that a lot.
Which, I mean, I didn't make the drawings, but I assume that is the reason for it.
Yeah. Oh, yes. 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 Yes.
Intuitive, as you said. That's good. But I do think that primes being some of the most wonderful and mysterious numbers in existence
Absolutely.
are another one of those things that are given or memorized as this is the set of prime numbers. Memorize all the primes up to however, and little thought or reflection is given to, but what does it look like? I mean, what does a representation of a prime number look like in, as opposed to the representation of a composite number? So it's very helpful, as opposed to just glossing right past it.
Were you going to say something, Kathy?
Yeah, it was kind of connected to my previous thought of how, Chris, I appreciated when you put the different factors on the blackboard up above when it was 2 and 2, and how in the notes, they're grouped. For example, the 11 in odd, right, isn't grouped by factors. It's grouped by, I don't know. But the even ones can be grouped by a factor. So those pictures could be 2 by 6, but the odds are not their factors, if that makes sense. Do I make sense? I guess my question is to the point of we can do 11, when you do the factor of 11, it's one line, as opposed
Yeah.
to there's no way that you could make that representation be similar to the even numbers.
Yeah.
It was just my thought.
On to the fourth.
Okay, fourth. Two numbers are said to be relatively prime if their only common factor is 1. The two composite numbers 9 and 10 are relatively prime.
Okay. Pull that in. Two numbers are said to be relatively prime if their only common factor is 1. The two composite numbers 9 and 10 are relatively prime. So this is a relationship between any two numbers?
Yeah.
The two numbers would be said to be relatively prime if their only common factor is 1.
Yep.
Okay. So
Kind of like Chris in geometry, two or more points are said to be collinear, like with each other. If there's a line that describes them, in this case, two or more numbers, said to be relatively prime if their only common factor is 1. So it's a relational definition in that you have to have more than one thing
yeah.
Described in the definition. It's a description of the relationship. Yeah.
Okay. So we could also add 7 in here.
Yeah. Those three numbers are all relatively prime.
Okay.
But in mathematics, we don't usually do that. We usually just talk about two numbers, but you can do it for more than two, of course. Right.
Okay. And then 9 and 10, of course, are not themselves prime numbers. It's just whether or not they have a common factor other than 1.
Yep. They're prime relatively.
Honestly, don't know if we covered that. We probably did, but not something that I remembered.
Yeah.
So
It's
is
in
that
modern
also
it's
that
in
8
modern
and 9
pre-algebra
would be
textbooks though.
relatively prime?
8 and 9 would also be relatively prime, yeah. But 8 and 12 would not be.
Is it true then that any two adjacent numbers are relatively prime?
Ooh, you're making theorems now. There we go. That would be a theorem that you could put into this book, and you have to prove
And
that.
test, right? Sure.
Yeah, good. That's what a theorem is.
Yep.
A statement that you can make about these things, and then you prove it. And these books are basically lists of theorems with their proofs.
Okay.
Good. Excellent.
Ready
Move
for
on
the
to the
fifth?
5th.
Okay.
It's like welcome to number theory.
That's right. 5th. The prime factorization of a number is the expression of a number as the product of its prime factors. Thus, the prime factorization of 12 is the product of 2 and 2 and 3. And then do you want me to get 6th at the same time? Or hold?
Yeah, go ahead.
And 6th. A number is said to be square if it is the product of two equal numbers. Each of the two equal numbers of a square number is said to be a square root of the number.
Okay. So let's pull 12 in here since we had that as an example. Don't have a drawing for it, so we'll make it. So prime factorization of a number is the expression of it as the product of its prime factors. And so in this case, we're taking 2 and 2 and 3. So I'm going to actually break this out further. We're arranging it as a product. So I'll scroll back up and reference. our product definition to make sure we've got it laid out correctly. Probably going to need 4. The product of 2 and 2 and 3. So the product of 2 numbers, first and a second, is the sum of the first of the second. So we have right here for 5 and 3, it's 5 threes. So 2 and 2 would be 4. 4 and 3 would be this 3 times. To give us 12. How would you lay this out, Mr. Jones, visually?
There's different ways you could do it. Some people like to make a cube out of it, 2 by 2 by 3. The way you have it right there is fine too. It's 3 groups of 2 groups of 3.
Yeah.
Yeah.
Oh, I see. The other way. Like this.
Yep.
So expressing it though as the product of its prime factors, I guess for you to have 2 and 3 both in that.
Well, the 3 comes, so in the purple example, right? You've got 2 times, you got 2 times 2, obviously, right? But you got
I
3,
see.
but you got 3 of those.
Right.
2 and 2 3 times.
Yeah. 2 and 2 3 times, right? Or 2 times 3 times.
I see.
And by the way, we haven't defined the word expression, right?
Right.
Probably the best definition of expression I've come up with my students is an expression is any representation of a quantity. But then, of course, you haven't defined representation, right? So these terms, expression, variable, those kinds of things show up a lot in algebra. I actually didn't originally have this definition for prime factorization, but teaching my 7th graders, they needed to know prime factorization, so I put it in. The problem with the definition is, of course, what do you mean by an expression, right? Because we're not really defining anything here. We're just finding different ways to express things, different ways to represent them. So we're not really defining anything new, so to speak. It's just a different way to represent these multitudes so as to show different relationships within them. So I don't really have anything better than the word expression, unless we want to go all out and define that as well. An expression is any representation of a multitude.
It took me a second to get this. I guess it's the 2 and 2 3 times.
Yep.
And
So
the
this
next
is-
one is equally tricky. It's 3 and 3, or it's 3 twice 2 times. I'm
Yep.
not sure how you can get away from saying 3 and 3 because it's not 3 and 3. It's 3 twice 2 times.
Yep.
And it's just this kind of
Obviously, though, there's a lot here that kids could play with, right? And just playing with
Yeah.
numbers like you guys are doing, right? And getting familiar with it. And that's where the skill of the teacher would come in. Like, how can I get students to think about these things? That's not what this book is meant to do, is teach everything, but gives the framework by which teachers can come up with creative ways to teach these things in a very hands-on method, where kids can play with numbers and see how they're arranged and see the relationships between these, between numbers.
Yeah.
This is just an outline, right? This is just a framework that shows that these things can be defined linguistically in a very organized manner. From there, a lot of curriculum could be written. which hasn't been written. This is not really a curriculum. It's more like a framework.
Okay.
I wish there was a
Um,
curriculum that had this as a foundation. That'd be much easier to teach from if you want to do it classically, right? That's the problem with classical mathematics today is there isn't curriculum that for which the content is classical. It doesn't exist. People can argue with me with that, but I can probably defend my position on that. There is no curriculum that's actually classical where all the terms are defined, because you have to start with the definitions and then build the curriculum, as opposed to just regurgitate what's been done for 150 years. That's what we're doing. Everybody keeps writing these textbooks with the same non-definitions over and over again, and then they say, well, let's just make this classical because we're having kids talk or something like that. That's not really how it works. If it's going to be classical, the terms have to be defined in a way that is rooted in reality, and the quadrivium is the only way to do that, and that's how it's been done for thousands of years.
I think one of my reflections on this whole process is the beauty of this and seeing it kind of, Bill, like what you're saying, it's almost like three-dimensional, right? You take these memorized facts, these little single dimensional things, and you give them body, you give them um, depth, and it allows it to be picked up, looked at, applied to, compared to the next thing. And so I think that really is what makes this so different, is that it just gives it more body to what it is that they're learning.
Well, people mistake consistency for concreteness, and they think that math is very concrete and not very abstract. But what they really mean is, I like that I can get the same answer every time. That feels concrete to me. But traditionally, math is an art. It's one of the liberal arts, and it is a very abstract concept symbolically, but its concreteness comes from the reality it describes. Uh, we've just dropped the reality and gone with the symbolic language, abstracted from it entirely, and then falsely call it concrete because it behaves predictably. Usually, until you start to play with it, and then it misbehaves. Like
Have we
all good
talked?
art.
Have we talked about the 7 liberal arts in these videos, Kathy? I don't even remember now.
At the first one, I believe we did, but it definitely doesn't hurt to repeat it.
There are
Lot
7.
7.
There are 7 liberal arts. 3 the trivium, 4 the quadrivium. Right. To state Bill's statement even stronger, right? It's not that math is one of the 7 liberal arts. It's that math is at least 2 of the 7 liberal arts, if not 4.
Not for him.
If not 4, depending on whether or not you define astronomy as geometry in motion, as magnitude in motion, as the ancients did, and music as number in relation, again, as the ancients did. If you do, then you actually have 4 of the 7 liberal arts, the entire quadrivium, mathematical. And it's so downplayed in modern classical schools. It's math is just another subject, and actually it's kind of ignored with respect to the classical renewal, because the classical renewal has focused on the humanities, and rightly so, because that's what was emphasized in the classics, because mathematics was taught as one of the humanities. A big shout out to Bill Carey, if he ever gets to see these videos. Bill Carey wrote an article in the classes called Mathematics as One as of the Humanities. Excuse me, Mathematics as One of the Humanities. In my opinion, the best article ever written about mathematics, and no one knows about it. It's just like a simple article that he wrote, and some people saw it and they loved it. He got an interview out of it and that kind of thing. And I know he's still working on different projects and stuff. Bill Carey, he's a young man. I think he's in his 30s. But he really nailed it on the head when he explained that mathematics is actually one of the humanities when looked at classically. So if you get a chance to read it, by Bill Carey, William Carey, in the classes called Mathematics as One of the Humanities. Best article I've ever read on classical mathematics.
I'm a big fan of that argument, and Jason Farley is working on such things as well.
Nice.
Yep, I think that we're we're gaining ground, but it's a slow battle. Math is definitely one of the humanities and four of the liberal arts. Well said.
I agree. As a music person, I agree. Definitely on the music. It is math.
But it's also not math the way we think of it. Modern uh, educators love to say, well, music is just math because they see symbolic manipulation and patterns. And they're closer to the truth than they realize, but they're not intentionally close to the truth. They are accidentally close to the truth. No pun intended.
Well, actually, speaking of music being math, being number and relation, which is what the ancients said, this is, I know from talking to Chris, this is one of Chris's favorite parts about this project is once you start applying relationships to things like numbers and magnitudes, the roof gets blown off this entire thing. And suddenly your understanding of mathematics just like it becomes a different world. Now, I've had students say to me, like, you've taught me to think in ways I didn't even know I could think, right? I'm like, yeah, I know. That's the point, is that once you start understanding how these structures work in relationship, you start seeing the whole world differently. And we're going to start that next meeting, actually, as soon as we get into integers. Chris, why don't you talk about that? Mathematics, music is number and relation. How does that relate to these books, Chris?
Okay. As a disclaimer up front, I struggled with musicianship at University High big time. But something that I guess similar is I do programming now, right? And the way I kind of see it is almost like being in a game engine, and you are able to observe the way things are being rendered, the way objects are being populated, and you're kind of able to start piecing together like these patterns. And based on your observations, you're able to kind of sort of start gaining insight into the underlying logic that is driving everything that you're seeing around you, right? It's like there's source code there that has logic and rules set in it that drive the way what you're seeing around you is like being rendered and being populated. And so in a similar way for us with mathematics, right, we are able to get at the heart of kind of the nature of things by observing nature, right? Like by observing reality. And once you gain insight into kind of that fundamental logic, those fundamental rules, you're then able to much more quickly grasp how that is affecting other disciplines and other things. Like we're doing arithmetic, right? That makes it easier to wrap your head around geometry, makes it easier to wrap your head around music, around like actual art and like sculpting. And I'm sure there's plenty of ways to apply this also. Like I know I can't give you any examples off the top of my head, but I know there are a lot of times where someone will find something out in nature or in science, right? And they're like, there's not a math formula for this, which will prompt the search for what mathematics explains this. And then you find the mathematics. And on the other hand, sometimes there's like just these mathematical findings just kind of sitting, in everyone's collective back pockets for decades. And then, oh, here's this thing we found in nature now that like matches up with this like perfectly, right? It's like the same underlying kind of source code. And like once you start to wrap your head around it in one way, you are then able to start applying it more generally. I mean, even just simple like logic and like problem solving as well, not necessarily just in like direct observations of things you actually see. I'm not sure if that's quite what you were after, but that's kind of what the conversation was making me think about.
Well, I was thinking more about how that relates to integers, which we're going to talk about next. But yeah, it covers it. And I was going to add say even thesis writing, writing papers, like the mathematics behind organizing your stuff is all mathematics. And I agree with Chris. Once you do it in one area, you can apply it to others.
Yeah. And then you see the patterns.
Yeah.
See the patterns all over the place.
That is one of the answers to how do you use math in real life that rarely got talked about. I remember I asked you one time, Mr. Jones, like, hey, like, I know it's the cliche question, but I'm curious what your take on it would be. And you gave me the example of like geometric I think it was factorials for like multiplication. And to this day, I still multiply in my head that way, or like divide in my head that like yeah, multiply that way. Where it's like, well, what's 83 times like 26? It's like, well, that's 80 times 20 plus
Yeah.
3 times 6, which like I wouldn't have thought to do that otherwise to like make that kind of connection. But once you start making the connections, they just keep happening.
Yep, breaking things down for sure. Well, next week we'll be answering questions like the big question that I keep harping on. And when Kathy invited me to speak in the Twin Cities recently, this is the question I asked everybody: what do we mean by an integer? We'll be tackling that question next time, because that's a mystery. Even to seventh graders who finish seventh grade, they still don't know what an integer is. They can't because it's not defined in the class. And I know that because if you're not looking at things quadrivically, you don't have definitions for your terms. It's really that simple. So I think that's a good segue for next time. Anything else you guys want to say? Bill, Chris, especially?
Maybe
We do
on
have
the
a little bit
notes.
left.
Yeah, I was gonna say we still should probably tackle squares and square roots.
Have we not finished?
I read them, but we didn't talk through them.
Let's do it.
Okay. So square numbers, a number is said to be square if it is the product of two equal numbers. Very intuitive. You can just see it, right, when you lay it out. Each of the two equal numbers of a square number is said to be a square root of the number. And so let me pull this in.
That's where the word square root comes from, right? The square root of 9 is 3. Why is that? Because 9 is a square number. It's very geometric, very historical. That's why we square numbers, like 2 squared. There's a 2 on top. It's a square because it makes a square. It makes the number square.
Back to the interest in special rectangles.
Okay. Well, that's the content.
One is an interesting one. Yeah.
1 is a square number. Yeah.
Mm-hmm.
How did we do, Kathy?
I think we did well. I was just thinking how, as I went over this concept with my seventh grade student this year, who is very visual and would have loved this idea. So you talk about, so kind of Bill, to your point, I talk about, well, this is what a square is, da, 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 but I didn't really help her to embrace what a square is in this with this visual format, or what the rectangular numbers, what that meant. It was really interesting when you see it visually. It's like, oh, okay, that makes sense. Moving on. I just think it simplifies it.
Another person who talks a lot about the interplay between arithmetic and geometry is Ravi Jain. You guys know who that is? Ravi Jain, this is his big thing, actually, the distinction between arithmetic and geometry. So he really works in my favor, I would say, because he's really made that clear that we need to distinguish these two, arithmetic and geometry. But that doesn't mean there isn't an interplay between arithmetic and geometry, as you can see, right? The geometric representation of numbers and the numeric representation of geometry. That's why the temptation to conflate the two into one was so prevalent in the 19th century, and they seized the opportunity because you can go so fast without conceptual understanding and build rocket ships and get us to the moon and win the great space race and that kind of thing, which has value, right? But unless you slow down and teach the students to think and to feel and to experience numbers, I think we're really taking away from that appreciation of how number can be understood through its beauty, not just through its function or its utility. They both have value, but that's the thing, they both have value. And so we need to slow down and remember the beauty in mathematics as opposed to only the utility of it. All right, guys?
All right.
There's a wonderful quote from Victor Hugo in the first book of Les Mis, in which the priest who has an important role in the musical and in the movie, but is much more developed in the novel, of course. I mean, it's like 1,000 pages. But when my wife, who is an artist, quotes this regularly. They have 3 garden beds in the monastery garden, and 3 of them are for vegetables and herbs, and one of them, he insists, is for flowers. And one of the ladies, who is very concerned with feeding the poor and caring for others, urges him to convert the flower bed to useful herbs and vegetables. He famously says, in defense of the flowers, the beautiful is as useful as the useful, perhaps more so. And so,
Good.
such is the case with mathematics, if only we knew.
Thank you, Bill. Thank you. Okay, well, I think that concludes book the 4th. We'll pick up next week with book the 5th. You're going to hear Chris talking a lot, I think, about the relationship aspect. He really does. He's talked about this. He's actually helped me teach on this to some of the teachers at the Summer Academy, the importance of relationships in creating different quantities and why it matters. So we'll talk about that next time.
Sounds good.
Thanks so much.
later.
It's good to be with you guys.
Thanks for your time, guys. Take care.
Take care.